This video is about two-body problems, and here's a picture of our first problem. And so if you can imagine, there are two masses here. The mass number 1 is larger, mass number 2 is a little bit smaller, and it's on a pulley, so with two cables or string on a pulley. And so there's actually a name for this kind of a situation here. We call this an Atwood's machine. I would assume it's after some guy named Atwood. You know what? Before I get to solving that question directly, I'm just going to back up and think about some of the stuff that we've done lately. When we first started doing kinematics, really most of our work was just some object that was moving horizontally, and we would say, say left would be positive and right would be positive and left would be negative. We got a little bit more sophisticated when we were doing projectile motion. So in projectile motion we had something going like this, and so we would often have this as kind of our origin, and then we would say, okay, now we have an x direction where this would be the positive x direction, and this would be your y direction, going up positive. Up was positive and down was negative, and things like that. So from the shift from this was one-dimensional, now this was two-dimensional, so we had an x and our y all the time. And then just lately we did this cool idea of an inclined plane, and then we said, hey, well, this object, the acceleration and its motion is going to be in this direction. So how about we define as going the parallel to the plane was positive and the opposite direction is negative. So it was a little bit like linear motion, except for we played around with which direction is positive and which direction is negative. So it turns out it doesn't really matter which direction is positive and which direction is negative, as long as you're pretty clear to declare it and you're being consistent in your question. So now let's go back to this Atwood's machine. If there's no friction involved in here, so this is going to be like a perfect ideal pulley and all this kind of system, and we're going to say, let's just let it go. So mass number 1, this was 200 kilograms. Pretty heavy, pretty massive. This is 50 kilograms. So which way, if this starts from rest, which way would it start to move? Well, I think it's pretty clear that this one's going to go downwards and this one's going to go upwards, right? That's the direction it's going to be accelerating. Now, the trick in doing this question is, and this is sort of the next step in our evolution of which way we're going to define as positive and which is negative, we're going to say that the direction of acceleration is positive and the opposite to the direction of acceleration is negative. So when we're talking about this object, we're going to say up is positive and down is negative. Now over here, this object is accelerating downwards, so we're going to say that down is positive and up is negative. And you might say, Mr. Spicer, you're not being consistent. Well, we're sort of thinking of this object together like that because they are connected by this cable. So this object, it will be accelerating upward with the same amount that this object is accelerating downwards. If we make this positive and if we make this direction down as positive for the other one, it has the same positive acceleration, and it makes things a lot easier. Okay, with that being said, let's take a look at our first method here, and this is the easiest method, and I call this the system approach, because we're going to think of this as one system. We think of, even though there's two different masses here, we're going to think of it as kind of like one object. So what happens when we think of it as one object? Well, first of all, the mass of the system is going to be equal to just simple m1 plus m2. So in this case, the mass of our system is going to be equal to, well, 200 plus 50, right? Now the F net of the system. Now let's consider that. Let's consider each of these objects, and let's draw a free body diagram from each of these objects. So can't erase that one. So for this object, we're going to have a downwards force of gravity. I'm going to label that Fg2 because it's object number 2, and it's going to have an upwards tension force. Now let's consider, how long shall I draw that second arrow? Should I draw it about the same? Should I draw it longer? Should I draw it shorter? Well, here's the clue. If I look over here and I say, hey, it's actually going to be accelerating upwards, that means the upwards force has to be greater than the downwards force. A lot of people think that those two are going to be equal, but they're not. So I'm going to draw, well, maybe I should try a little bit more yet. I'll draw it a little bit longer. than the downwards force. Okay, so there, that is the tension force. I'm just going to use a T. Now looking over to the other object, the key in these questions is that this tension force here and the tension force on this object is actually going to be the same. So I'm going to try that doing that same length. This tension force is in the positive direction. This tension force is in the negative direction. So when we consider the whole thing as one object, those two tension forces are going to cancel each other out. Another way to think of it is that these tension forces are internal. So when I'm thinking about this as one object, then these tension forces are internal. It's sort of like, I don't know, if you're in a car going down the highway, right, and you and your brother or sister are pushing on each other here, you're having a little fight inside the car, this whole car is going this way. These internal forces, you pushing on the other person and sibling when you're, fighting in the back seat, is not going to affect the motion of the car. It's going to just affect your motion inside of here. So this pushing on this object would just be an internal force. It wouldn't be like an external force acting on that car. So these tension forces are internal and they do not contribute to the F net of the system. So finishing up the free body diagram of object number 1, we wrote the tension force going upwards, and now I'm going to make a force of gravity force going downwards. Again, I'm going to ask myself, what should the length of the arrow be? How would it compare to the tension force? Well, it's accelerating downwards. So in other words, the downwards force has to be greater. So I'm going to write Fg1 downwards. Note my Fg2 was smaller. My Fg1 is a lot larger, but that makes sense because the mass of object number 1 was only 50 and the mass of the mass of object 2 was 50 and of object 1 is 20, so that the lengths of those arrows are going to be different. So now when I go over here to F net of the system, I'm going to not consider the tension forces. I'm just going to think about Fg2 and Fg1. Fg2 is in the negative direction, Fg1 is in the positive direction. So I'll say Fg1 minus Fg2. Right? Because Fg2 was in the negative direction, so it's a negative. Now if I wanted to actually calculate those, the force of gravity is the mass times 9.8 minus this mass, which was 50, times 9.8. I might even consider and say, hey, this is the same thing as 150 times 9.8. Now, we're almost there. How do you figure out the acceleration? There's two things we have to do. We have to figure out acceleration, that would be part A, and part B is to figure out the tension. So we're kind of on the part A section over here. So to figure out acceleration is equal to F net over m. So in our case, it's the F net of the system, 150 times 9.8, all divided by the mass of the system, which we figured was 250. So 150 multiplied by 9.8 divided by 250 turns out to be 5.88 meters per second squared. So there's one of my answers. I'll put a box around it so Mr. Spicer can find it. Now for part B, I want to know what the tension is. Now to do part B, to figure out the tension, in this system approach, there's no tension forces, right? Because the tension forces were internal and they don't show up. So we can't really use this system approach. Now what we have to do is draw free body diagrams of each object, or consider the free body diagrams. And I know I kind of wrote them there already, but I'm going to write them here. So now when I figure out tension, I need to draw FBDs, free body diagrams. So free body diagram number 1, that one's easier. It is just a force of gravity downwards and this tension force upwards. The force of gravity, now I'll write an F net statement. F net equals MA. So again, because it was accelerating downwards, the downwards direction is positive. So under F net, I will write, what are the sum of the forces? Well, it's Fg1 minus tension. It's going to be equal to mass of object number 1 times acceleration. So plugging in what we know, the mass of object number 1 was 200 kilograms. So this would be 200 times 9.8 minus the tension force is equal to 200 times 5.88. Now I think in this example, 5.8 was every single decimal. If this had been some decimals that kept on going, I'd use the memory feature in my calculator. In any case, now when I finish all this work, let's see, 200 to, well, I would like to get t by itself, so I'll add t to both sides, and I'll subtract this 200 times 5.88 on the other side. So I'll get 200 times 9.8 minus 200 times 5.88 equals the tension force, and I get an answer of 784 newtons. You may say we're done, but we have a built-in check here, because at the beginning when I said draw a free body diagram, there are two objects, and I just only used object number 1. So what I can do now is use object number 2 as my check. So object number 2 has force of gravity 2 and has a tension force upwards, and this object is accelerating upwards. So my tension force will be my positive one and my Fg2 will be my negative one. So if I write F net equals ma, I'll get tension minus Fg2. Again, because if I'm accelerating upwards, my tension force is in the positive direction and the force of gravity is in the negative direction. It's going to be equal to m2 times a. So my tension force minus the mass of object number 2 was 50 times 9.8 will be equal to 50 times 5.88. And when I finish all my work, I do get a tension force again of 784 newtons, and that makes me happy because the check was good. Okay, so there's an example of how to solve this using this system approach. We did two things. We found the acceleration and we found the tension force. Now we're going to do this entire question again. We're going to do it, if that was the easy way, and you might say, really, that was easy, that was a lot of work. The second one is slightly different. It's a little bit more mathematical. It's with doing individual free body diagrams. So we're going to do the same question again, and this again was 200 kilograms. This was 50 kilograms. And so what we're going to do is we're going to draw two free body diagrams. So our first one was the tension went up, Fg1 went downwards, and we're going to use that same idea about which way it's accelerating. So this is going to be accelerating downwards, and this one will be accelerating upwards. So again, I'm going to say, when I draw my F net equals ma statement, I'll say Fg1 minus the tension force is equal to m1 times a. Now I can plug in all the numbers that I know. I can say 200 times 9.8 minus the tension force is equal to 200 times a. You know what, I'll even do the 200 times 9.8 here. I'll say 1960 minus the tension force is equal to 200a. So that's as far as I can get because I have an equation. I have an equation with two variables, and I can't solve that. So I'm just going to stop here, and I'm going to say that is equation letter A. All right. Now I'll go on to FBD number 2. And similar to before, I'm going to draw this. I'll say, okay, we've got an Fg2 downwards and a tension force upwards. In this one, however, up is positive, down is negative. So when I draw, maybe I'll switch to green here. When I draw F net equals ma, and now my tension force is positive, Fg2 is negative, my mass is object number 2. I can type in everything that I know. Oops, it's supposed to be a minus. Minus 50 times 9.8 is equal to 50a. 50 times 9.8 is equal to 490. And I'll stop there because that's as far as I can get. So now this is a classic math problem where I have two, it's called a system of equations, where I have two different equations and they each have two unknowns, and I would like to do something to solve the unknowns. So looking at this, I'll say over here, well, if I take A, and I'm just going to move this over here. Actually, you know what? Here I've got a t and there I've got a minus t. So I'll put my b first on the top. I'll say t minus 490 equals 50a. And then underneath, in blue, I will write this, but I'm going to rearrange this. I'll put the minus t first, plus 1960 equals 200a. And I hope you see where I'm going here. If I add these two together, t and negative t combined together is no t at all. So those two cancel each other out. Minus 490 plus 1960 is going to give me 1470. 50a plus 200a is 250a. And now we're almost there. We just divide both sides by 250. So I say a is equal to 5.88 meters per second squared. So it took me a little bit longer to get acceleration. I did say that that system approach was easier. Now, so part B, where I have to find the tension, now I can go to either of these two formulas that I already had, and I should say I have A. All I need to do is find out what T is. So I'll take equation A and I'll substitute my acceleration in there. So I'm going to say 1960 minus tension is equal to 200 times 5.88. Just to save a little bit of time, I'll say, hey, I do get the right answer. I get T is equal to 784. And just like before, we can do, in part B, we can do a check. And we can use equation B and do the same thing. And we say T minus 490 equals 50 times, and we found out what A was. And we get the same answer. T is equal to 784. I'll put newtons around it this time. So my check works out. Okay, so solve the same question two different ways. And we got the same answer, so that's kind of nice. Hope you're keeping up, because I know that was a little bit complicated. Let's try example number 2. So in example number 2, it's a little bit different. We still have this hanging mass, and we still have a cable, but now we have this object is going to be moving horizontally, and this object will be moving vertically. One neat thing here is we have no friction. So let's consider which way this will be accelerating. Well, this object is going to be accelerating this way, so we're going to say that's positive and that's negative. This object will be accelerating to the right, so we'll say that's positive. Here, maybe I can make it neater. So we'll say this is positive and that's negative. Okay, so let's try the system approach here. So we're going to say, what is the F net of the system? Well, considering the free body diagrams of each one, this will have force of gravity, number 2, and it will have a tension force, and the tension force will be a little bit shorter. This one will have that same tension force to the right, and then it'll have a force of gravity, number 1, and a normal force upwards. So, considering all these, well, this normal force and this force of gravity number 1, they're going to be canceling each other out because they're in equal length and they're in opposite direction. This object will not be accelerating vertically, so those vertical forces are going to cancel each other out. The other piece is that these tension forces cancel each other out because those are internal forces. This tension force is in the positive direction, this tension force is in the negative direction, so they indeed cancel each other out. So this is actually kind of a simple piece here. The F net of the system is merely the force of gravity of object number 2. So what is that mass? This one was 20 kilograms, so it's 20 times a 9.8, which would be, what, 196? You know what, I'll just leave it as 9.8 for now. Now the mass of the system is going to be equal to just 20 plus 250 270 kilograms. So my acceleration is going to be equal to F net over m. So this would be that 20 times 9.8 all over 270. So here's where I get 0.726 dot 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 meters per second squared. Guess what I'm going to say? Yes, you got it. Put that in the memory because we're going to be using it again. Alright, now the second part is the tension. Just like before, we're going to look at one of the individual free body diagrams. So to do the tension force, I don't know, let's try free body diagram number 1. So here's my object. I had Fg 1 downwards, I had the normal force this way, and I had this tension force that way. If I write an F net equals ma statement for it, these two cancel each other out, and I just have that tension force, which is equal to the mass of object number 1. The mass of object number 1 was 250 multiplied by 0.726 in all the digits, because I'm just multiplying that from the memory of my calculator, and I end up with 181.48, which will, after rounding off to 3 significant figures, 181 newtons. Is there a check involved? Of course there's a check involved because we have a second object. So if we go back and say, what's the free body diagram for object number 2? Here we have Fg2 downwards and a tension force upwards. So looking at my F net equals ma statement, well, which way is positive, which way is negative? Down was positive, up was negative. So we'll say Fg2 minus the tension force will be equal to the mass of object number 2 times the acceleration. So Fg2 was 20 times 9.8 minus the tension force will be equal to 20 times 0.726. I'll just quickly say that my answer ends up being the tension is, again, 181.48 newtons. So it works. So it's very nice. Okay. Here is your U-turn. No, sorry, your turn. Give it a try. And it's very much like our last one, except for all I did was change the masses. So hit pause, try it out, and then I'll show you my answers. Okay, so here's my answer. The acceleration is 1.4 meters per second squared, and the tension is 8.4. You'll notice that this object goes to the right, this object goes down, so that's the directions that we're going to choose. You can take a look at and see how you did. For our last example, we're going to introduce a little bit of friction. And let's use this last question, but introduce friction. We're going to say mu is equal to 0.4. What happens? Well, I guess the first thing that happens is when we look at this, we have tension to the right. We have this Fg1 downwards. And we have the normal force upwards. And now we're going to have, if it's starting from rest and it's starting to move to the right, the friction will oppose the motion and we'll have a force of friction this way. Let's just think, what is that force of friction going to be? The force of friction is going to be equal to mu times the normal force. The mu, we're told, is 0.4, and the normal force is going to be the same thing as the force of gravity. This is m1 times g. Object number 1, what is object number 1? Is 6 kilograms multiplied by 9.8. So this force of gravity, or this force of friction, pardon me, will be 23.52. Looking at our other ones here, we have this tension force upwards, and we have this force of gravity number 2. The object number 2, force of gravity number 2, this was only 1 kilogram. So let's think about which way. We were assuming right away that this object is going to be accelerating like this because the hanging mass. And let's just consider what the numbers are telling us. This is telling us that of all the forces, this force, force of friction, or force of gravity number 1, and the normal force are going to cancel each other out. And then these two tension forces are going to be canceling each other out. So all we have left are this force of gravity number 2, which is 9.8 newtons, which is pulling them in the positive direction. Opposing it is a force of friction, which is 23.52. So which would win the battle, so to speak? This pulling down, this force of gravity number 2 of 9.8, or this force of friction of 23.52? According to the numbers, the force of friction would actually win it, and it would accelerate this way. And now this seems a bit absurd. How could this block start accelerating leftwards and pull up this hanging mass? So the way this formula of force of friction works, this is the maximum number that it could be. So if this hanging mass was larger and larger and larger, the force of friction would still stop it from moving. So if this number is larger than that number, then what we would say is there's not going to be any motion. It's not going to move. The force of friction will be just exactly enough, 9.8, to stop it from moving. So why don't we change this question? We're going to change this question so we can actually solve it, where we can have a more exciting result than, say, no motion. So here's what I propose. Let's change this number here, and let's change mu to 0.04. Because if we're going to only have a 1 kilogram mass here and a 6 kilogram mass there, and we still want things to move, let's do that. So this 0.4 becomes a 0.04, and then this 23.52 will turn into a 2.352. And then what will we get for our F net of the system? Well, we have Fg2 in the direction of motion, and we have opposing it the force of friction. Like I said, the tension forces are canceling each other out, and the normal force and that force of gravity is canceling each other out. So we'll get 9.8 minus 2.352, which comes out to 7.448 newtons. My acceleration is going to be equal to the F net of the system divided by the mass of the system. So I'll take that 7.448 and I'll divide it by the mass of the system, which is 6 plus 1, which is 7. And I get an acceleration of 1.064 meters per second, or if I round that to two significant digits, I get 1.1 meters per second squared. So you'll notice that when there wasn't any friction, it was accelerating at 1.4. And now when I introduce just a little hint of friction, just 0.04 coefficient of friction, now I'm all the way down to 1.1 already. The last step is to find the tension. And we can take either of these free body diagrams. If I take equation number 1, and I think, okay, in equation number 1, and I have to do an F net equals ma statement. What is the F net? Well, the normal force and the force of gravity are going to cancel each other out. I've got the tension force in the positive direction minus the force of friction is equal to the mass of object number 1 times acceleration. So I already figured out that friction force was 2.352. That's a minus 2.352. Which is going to be equal to the mass of object number 1, which was 6, multiplied by the acceleration of 1.064. And I get a final answer here of tension is 8.736 newtons. When I look at object number 2, and I do an F net equals ma statement for that one, for object number 2, I have force of gravity number 2, which is going in the positive direction, minus tension in the negative direction is going to be equal to mass times acceleration. The mass of that object is just 1, so I get 1.064 for m times a, and here I'm going to get 9.8 minus the tension force. So my tension force is it's a good check because I get the same answer. Okay, a lot of good stuff that we learned here, and we're going to see you on Tuesday, or if this isn't the same year that I made it, we'll see you next time in class, and we'll do some practice questions.